Welcome to lesson 3. In the previous 2 lessons, we went over how do we get started with FastAI and how do we explore moving away from the data block API into PyTorch datasets and really removing the library as a whole. And so today we're going to go more into the framework itself. We're going to cover multi-label classification and what that really means. What do you do when you're trying to recognize a class that isn't part of your training set? Or another way to put that is the unknown label problem. And then finally, we'll touch on cross-validation and ensembling a little bit. This is going to be a lot of the same sort of stuff that we saw in the previous iteration of the course, but explored from a lower level API. And then next week, we'll get a bit more into the fun things outside of just mild rehashing with a bit more stuff. To start with, we're going to talk about multi-label classification. And what that means is, say you have an image of a cat and a dog. Currently, all we know how to do is take a model and train it to say, this is a picture of a dog or a cat. We're going to try and train a model that lets us take both of those labels into account. Now, what you'll notice from here on out is I have the from fastai.vision.all import star here, but then right below it and for every single lesson afterwards, we're going to have the full imports for everything we're using. This is going to be where in the fastai library it is. If something was monkey patched, it's going to have this little comment of what it is and where it came from, along with the original import. So here you can see we have 2 imports for the fastai learner so that you understand this is going to bring in specifically patched learner functionalities. This goes back to that 2 ways to import patched functions that I mentioned last week. So the first thing we're going to do is obviously download a dataset like we normally do. For this particular problem, we're going to use the planets dataset. It's a collection of satellite images with labels based on coverage and, well, really cloud coverage and what is inside of the picture. As per usual, we'll download the data. And then in this case, the data is part of a CSV file for the labels. So we'll go ahead and open that in pandas. So if we take a peek, you'll notice that we have an image name column and a tags column. And in this case, the image name doesn't have an extension or a file path. So we're going to have to be a bit creative on that one. And then our labels are separated by spaces. This first data point here has 2 labels, right? Partly cloudy and primary. The second image here has clear, cultivation, primary, and water as its labels, and so forth. We can take a look and see how the labels are sort of distributed if we want to do a little bit of EDA. So first we can see how many total labels there are in general. This includes repeats, and there's almost 2,900 labels, which is a lot. But if we look at how many different labels there are by looking at the unique set in all of that, there's only 17. So much less than a few thousand. What we can then do here is this little code chunk takes all of our labels, counts the number of occurrences for a particular label, and generates a new dictionary off of that before finally sorting them all. That's what this sort of code block does here, and there's obviously the code and explanation tab you can look at later. And what we'll find is most of our labels have primary. Hey, everyone, nope, you haven't missed anything yet. We're just going into the exploring of the data for multi-label right now. So most of our labels are this primary tag, and then we have clear, agriculture, and road, which as we go further down has a very steep offset we can see in our labels until we get to the bottom and we have these ones that don't really show up very much, like selective logging, artisanal mine, slash burn, conventional mine, and blowdown. When we are training the data, if we don't do anything for this, somewhere down the line, you're going to get a key error when you train with FastAI. And basically what that means is some of the labels only exist in the validation set and don't exist in the training data set. For instance, this single instance of blowdown, if we randomly split the data, there's a 1 in n chance, which is really small, for it to only wind up being in the validation set, say if it's 80-20. There's a 20% chance of that. But that's still 20% where it's just magically going to give you an error. And vice versa, if we do include it in the validation set, it's never going to be trained on. So for this, we're going to take everything that shows up less than 9 times, so selective logging and down, and basically get rid of them. There's a few other methods you can do that I've sort of talked about over here, something called oversampling, which works quite well. And basically what that does is it takes these values that aren't represented as much, as long as they're in the training data set and the validation data set, and duplicates the training samples to sort of give them more times to be looked at in a single epoch. The important note for that, though, is you should only oversample on the training data set and never on the validation. I have a few resources, I believe, in the old course on that, and I can link some as well in the Discord if folks have questions or want to learn more. So next, given this sort of count, we'll take our original 1,000 rows and check if any of them are less than 10, where they show up less than 10 times. And we can do a selective filtering here, like we saw last lesson, to basically keep only the columns that don't have whatever value that is. And so we got rid of a number of classes, right? Less than 10 gets rid of blooming, logging, artisanal, so 6 classes. And while that got rid of a lot of them, we only really got rid of 32 rows. So they were very rare samples that didn't show up very much, even combined. And so in the real world, rather than doing this, ideally you would try and get more data from these underrepresented groups or labels. In this case, though, since we can't quite have that, rather than have our model potentially be biased towards something that never shows up, or have it train on something we can't actually validate it on, we're just getting rid of it. Now, if we look at these images, right, I mentioned all we have is the file name. We don't have anything about the extension. So in that data path that we had, there's a folder called train. And inside this train, so we have .fastai. This is that cache where all our data sets are stored. The name of it, the name of the data set, the training data set, our image, followed by .jpeg. If we open one up very quickly, you can see that it's a pretty gray blob. If you're unfamiliar with satellite imagery, a lot of it looks like gray blobs, and you try and find the non-gray blobs in the blobs. Typically, you do things like image segmentation a lot with satellite imagery, using tools like ArcGIS and bits like that is really where this comes in very handy, which ArcGIS has worked with fastai actually in the past. But now that we have the image, we know how to find the image, and we know how to get the labels, we can work on building a datasets object. So based on what we know, our X's are colored images, so we'd probably want to use PIL image, and our Y's are multi-labeled images, meaning that rather than categorize, we want to use the multi-categorized transform. Next, when it comes to getting the items, we're going to do a bit differently this time, and we're going to write a series of getters where it looks on a single row of our data. And specifically, our X's are located in source, train, and some file name. And so that can look at our image name when we write that function. And then our Y's are split strings, and that too can be written as a function. And I have a little note here. But the reason why we have these as direct functions is typically what you'll see instead, especially in fastai notebooks, is they'll use lambda instead, which lambdas are what's called an anonymous function. It simply means it doesn't have a name. It exists so long as it is called in that instance. So I can't write lambda x print x and then label and then later call like x because it has no name, right? It's anonymous. But that runs into trouble when you try and export your learner or do anything with it, because you're going to get this weird XYZ can't pickle lambda blah, blah, blah. And this is because lambdas aren't really pickleable. They're becoming more and more pickleable as time goes on, but also that's very dangerous, and you shouldn't really pickle lambdas at all, let alone functions. I'll link a useful bit in the Discord about data compression technique or saving technique that Hugging Face has been developing. It's a different way to do things besides pickles. But the important thing with that, beyond just self-promotion of Hugging Face, is it was written by Sylvan, and it compares a lot of the different file formats that a lot of different libraries use. And so you can kind of learn from that just why pickles are so bad, especially from a security perspective. And then finally, there is no real set value for what is trainer validation in this subset we're training on, so we'll just randomly split the data. So if we were to build everything, we'll define a getX here that takes in a row, which is called a pandas series. It'll return a path, and we're going to return basically that file name with the suffix .jpg. And with suffix, we'll either replace or add the suffix to the last item. So this will just add that .jpg at the end of it. And then for our get y, it's going to take in a series, return a list of strings, and we're just going to say split by spaces, right? So if we test it out very quickly here on a single row, we get back the file name we want to train on and the fact that it is both partly cloudy and primary as its labels. Now, this is how we write this as a function, right? But we can also write this using the fastai API through something called the call reader class, which takes an index, potentially adding a prefix to whatever it gets out of that column, and a suffix out of whatever gets to that column. And similarly, you can attach a label delimiter to it too. So if you wanted to stay with fastai, you could use call reader, or you could write 2 lines of code and create your own functions. I'll sort of leave that up to you on a preference. I don't particularly care one way or another. Personally, it's whatever gets there faster. Now that we have all of that, we can start by preparing our transforms. So we're going to make our get x, pass that in, and then say after our get x, we want to do pil image create. We'll make our y's, go through get y, convert into what is called multi-categorize, and tell it just what all the labels to use are. And then because we're doing multi-label as well, we're going to do what's called one-hot encoding the labels. So rather than it just being 0 and 1, for instance, what this really opens up in the labels is it's sort of binary. So before, when we did classification, right, it was one answer of 0, 1, 2, 3, or n. With one-hot encoding, what that then does is say we have 5 different labels. Those 5, for one label, let's say it's the third class, instead of it being 2, right, because index of 2, it would be 0, 0, 1, 0, 0 as the label. Basically saying, okay, this label is present. We're going to use it sort of as a binary, is it there or not for each label. And so that's sort of how we treat multi-classification different than single label classification. And that's really all that there is to it outside of that. Besides just changing our loss function, nothing really crazy has to happen between single versus multi-label. And then we'll get our training and validation indexes by just using the random splitter, 20%, and a steed, and then pass in our data frame. The splitters all work by having anything that is iterable be passed in to get those indices. So we can just pass in the data frame itself to generate those. So we don't have to pass in like range length data frame, for instance. We can just say data frame. And now that we've made all of our transforms, we have our splits, we can create a datasets object and take a peek at it. So we have our PIL image, right? And it's a 256 by 256 image. That's what this entire dataset is. And then you can see this sort of one-hot encoded label I mentioned earlier. So it's got label 2 and label 7, I believe that is. And this label and this label, the rest of them are not present at the bare minimum. And we can use the showAt function to let us see what a fully transformed image looks like. And we can see that it's clear and primary, and this is our image, which we saw earlier. All right, so the last thing we need to do is build some data loaders. Now, as we've sort of seen before, the datasets objects have a .data loaders function. So we just need to tell it what transforms to use. Now, because every single image is already sized at 256 by 256, we don't need an item transform to crop the data, really. You can do pre-sizing if you want, but in this case, we can just go ahead and use toTensor as the only item transform. And then for the batch transforms, we'll do some basic augmentation into float tensor and normalizing. And we're going to use a pre-trained model for this, so we need to normalize from ImageNet stat. And then we can see that if we look at a batch of data, it's a little hard to read here. You can pass in DLS show batch and pass in a figure size. I believe there was an example in a previous lesson showing that. And that'll make this a bit easier to read because some of the labels are so long that they just go over each other. But the good news is all of this looks about right. So you can see that we've got like trees over here, forest over here, a cloud here, and that all looks to be about right. Let's see, there was a really good question in the chat of when we are building data loaders, And after item, how is it that we can just pass to tensor and we don't need to instantiate the class? Because this is a class due to the naming convention here. And the reason for that is fastai will do that for you. That's the only reason why, really. It's an interesting thing where we don't really have to care, and there's nothing really else to that. So you could call toTensor with parentheses and instantiate it and whatnot, or not. It doesn't really matter. The main places it matters is when you're trying to do something like normalize from stats. Then you care about the sort of calling the function afterwards. All right, now that we've created some data loaders, next we'll go to training a model. So similarly to everything else we've done before, we can just call learn equals vision learner, pass in our data loaders, pass in a ResNet. And then in this case, we can't use accuracy because accuracy is right or wrong for one label. That doesn't really work very well. So fastai has a metric called accuracy multi, which is, as it sounds, accuracy based on multi-label classification. One thing you'll see here as well is our head did not change, despite the fact that we're doing a completely different classification problem. It's still just a linear layer because the multi-label happens based on the outputs from the model. And we can see that in our loss function. So the loss function for our learner was changed from flattened loss of cross entropy loss flat to flattened loss of binary cross entropy with logits loss. And basically the difference to this is rather than having that softmax that converts everything to a percentage, we could do what's called a sigmoid operation instead, which sort of scales it all. And then we can say what is present or not based on a threshold. And that threshold by default in fastai is 0.5. So in this case, if our threshold was 0.5 and this was just our model's logits, we would say that every single label was present. Now, a really important thing to note about this, though, is when it comes to your metric and your loss function, they should have the exact same threshold most of the time. Because otherwise, you're going to look at two different things. Because the loss that you have here, if it's, say, set to 50% versus your metric is 30%, your model's not going to be training to try and get 30% and improve more. And so it doesn't quite match up in that sense. And the way you do this is you just override learn.lossfunction.thresh to be whatever you wanted to pass in when you also do similarly with accuracy multi, which for this, you can look at the docs for accuracy multi, but this is going to be another partial function where we override it a little bit. So it's going to look something like partial, I'm not even sure if you can see this very well, accuracy multi-thresh equals blah. You probably can't see that too well, and I'm sorry, but hopefully it somewhat is there. So now that we have a threshold and we've built our learner, we can just train like normal. So we'll do LR find and find a learning rate roughly 2e-3 is pretty good. Train on it, get an accuracy of 60%, unfreeze, and train some more. I've made a little note here as to how this weird number came to be. And basically it's Jeremy's best practices when he was training ULM fit that also works quite well in general when we're doing fine tuning. And if we look at the results, we did pretty good. Show results shows that we pretty much got 3 of these right, a few of these wrong because we were missing just 1 or 2 labels. There was a question of what if we are using AUC or area under the curve? Threshold doesn't apply. In that case, yes, because area under the curve is a different metric than and loss function in general compared to CE. Well, metric. And then let's see. There's a question of not immediately relevant, but could I expand on flattened loss being used in fastai versus the typical loss for no flattening? Literally, it's just to prepare it for metrics. Like toy around with flattening versus not flattening of the outputs, pass it to the same loss function, and then try using metrics, and you'll sort of see what happens. But fastai doesn't like that, to say the least. All right, so now that we've trained a model, right, let's look at what inference looks like. So we're going to remove fastai here. Again, we're going to get the model, get a file name for us to use, and open it in Pillow, convert it to RGB, convert it to a tensor. And then this is what int to float tensor is. So it converts it to float, divides it by 255. This converts it into a batch. And then we're going to do some normalization on it. This is some interesting vector matrix multiplication. I've linked to the first lesson from Deep Learning from the Foundations, simply because it goes into this briefly and it's good to know about. We can see that afterwards we have our mean and standard deviation are the shape that fastai wants it to be. Make sure. Earlier, for the getters, I was curious if a type must be set due to type dispatch. No, unless something explicitly inherits the fastai transform class, it doesn't. Let me make sure. Yeah, it doesn't. And we'll cover type dispatch and everything in lesson 7, because that's one of the biggest pain points in fastai. So I want to make sure that we talk about that a bit before any of you maybe go on to running. And if you don't, you at least are familiar with it. Afterwards, we can normalize the data. This is how fastai does normalization. So we take the image, track the mean, and then divide that by the standard deviation. Now we have a batch of 1 with a 3-channel image of a certain size, and we can get some predictions. Now you'll notice I use torch inference mode instead of torch nograd. Inference mode is slightly more computationally efficient than nograd. Say slightly. So like if you want to just use it so that way you have everything and not worry about it, just use inference mode. We'll convert the model to eval to make sure nothing is set like it's training, such as batch normalization, and get some predictions. Now, once we have these predictions, how do we convert that back into how fastai does the whole, these labels are there, these labels are not. So we'll apply what's called a torch sigmoid on them first, right? And then we'll add this little conditional here that basically tells this tensor, become a bunch of booleans. And you're true or false, depending on if you're greater than 0.5, which 0.5 was our threshold that we set earlier. So now in our decoded predictions, we can see that this label was present and this label was present and the rest of them weren't. Now I have a little code snippet here using ITER tools. And basically what this does is very quickly converts this Boolean tensor into our labels again. An explanation over here for that for you to read on, but we can see that it's partly cloudy in primary. And then if we convert it and predict ourselves based on fastai, we also get partly cloudy in primary. So we successfully recreated how fastai predicts again, this time for multi-label classification. And the thing to note here that was different than everything else is we had to worry about how the loss function decodes predictions. Because when fastai decodes things during predict and get preds, it doesn't just decode transforms, it also decodes based on the loss function, which is very weird for the library when you think about it, because loss functions aren't a transform, but that's how the API is built. So it has a decodes that it can use. Now, very quickly, I've just linked how you can perform all of this as a little copy paste snippet for you here in case you ever want to go deploy this. But if anyone has any more questions, I'll take them now. Otherwise, we'll take a 5-minute break for a moment and go on to the next part. All right, we're about at the 5-minute point. Let's see if we have any questions. Looks like we don't so far. So we'll go ahead and keep chugging along. All right, so the next part is looking at identifying unknown images. Another way to think about this is the unknown label problem. And the general idea and issue behind this is a lot of people want to know, okay, so I've trained a model and it can identify hot dog or not a hot dog, for instance. We'll take a very basic example, or cat and dog. But what if we have a picture of a pear in the hot dog, not hot dog, or in the dog cat, we have a picture of a parrot? Well, because of how that softmax and argmax works based on what we saw earlier, our model will try and predict how it fits in the classes it was trained on. And then when we do that softmax argmax, it will always try and take those predictions and find what it belongs in, even if the probability of it being that is unbelievably small. So how do we fix that? Well, we can sort of hack it a bit. So when we did multi-label, right, it gave us a tensor of n long from 0 to n. Well, what that also enables is, because it's sort of this Boolean yes or no if it's present, none of them can be present. And so what we'll look at today is how we can take this idea of, hey, this is a model that in a sort of situation and setup that can tell us if nothing is there, and adapt how we prepare our fastai dataset to let us train a model that essentially will tell me, I don't think I know what this is. I've included the transforms here again. There's a little bit more in this one than the last one because this is going to be another, we'll look at the data block API before going into the datasets API problem. But let's get started. So as always, with when we want to introduce a new ID, we're going to start with the pets dataset since we know and love it. So this should all be very familiar for you. We're just creating a basic data block. And what you'll notice here is like right now, this is set to single label, right? Because it's category block. And we have a get y that returns a single label. Now, I'm going to show you a quick 2-line hack that lets you take this problem and convert it into multi-label. The first step is write a simple transform here called label to list. I say transform, we'll say function. And label to list just takes our label and returns it as a list. And so what we can do now is in our get y say, all right, I want it to be a pipeline of our regex labeler, and then based on the output of this labeler, convert it to a list. And this could be lambda x parentheses x, but remember we want to be able to pickle things, especially if you do choose to stay with the fastai API. So that's why we converted this into a very small function here. And I didn't describe it or document it a lot because it's very straightforward. And usually the user wouldn't see this. And it's not something where if someone saw it, like, oh, what the heck does that do? But that's a whole design philosophy part that I'll go into in a later course. Otherwise, everything else is exactly the same. So we just changed category block to multi-category block and changed our get y, and that's it. So if we create a new set of data loaders, since it's one label, it just looks like exactly what we had before, right? Samoyed, Newfoundland, Basset Hound, Shiba Inu, and so forth. But because we use multi-label under the hood, when we start decoding, it will be able to pick up on, hey, I don't think this is any of them. Now, here I just show what that's going to be like from a multi-label classification or from a datasets perspective. So it's going to be regex labeler or label to list, and then bring in the stuff that multi-category block does. So this is what we looked at a moment ago. And we can see that if we check our outputted tensor in the dataset, we only have one answer that is a 1 because there's only one right answer. Then we can create some data loaders, add in some transforms, and basically be on our way. Now here we're going to take what I sort of mentioned earlier with the threshold and bring it into practice. So with our problem here, I'm going to say that our accuracy only matters if the model is really, really, really confident that it's the right answer, right? So 95%. And actually, I believe threshold is lower in this case. I have to go back and look at that. But this could be backwards and the threshold should really be 0.5. Otherwise, it's saying it's always present. But we didn't change our loss function. And so now we'll see like, oh, our training loss was kind of high. Our validation was kind of low. And our accuracy was super, super high. I mean, this is a very different number compared to this one, right? And it's very different than what we saw earlier. And this is sort of that discrepancy that can happen because it leads to, this actually isn't that accurate of an accuracy metric compared to how our model is being trained. And so it leads to these very, at first glance, really good numbers, but unless how each of these are behaving and unless they're aligned, they're not really correlated with each other. And you can't treat them the same like we could before. So this is basically how we would apply that. We would set the threshold to be 0.95 in the loss function. Now, I'm not going to retrain with that on there. We're just going to see what happens. But we'll predict with one of our classes, or an image specifically from one of our classes. So this is a Peruvian cat. We'll download it with the request library, open it up in a pillow image, and predict. And you can see that it successfully figured out this is a Parisian cat. Now, what happens if we try a donkey? Which if we open this up here, you can see that it's just a picture of a mule. It didn't say it was anything. And this is because the threshold of when we said I believe that this answer is something you can say it is, that 0.95. It never reached that threshold for any of the classes. So now we successfully have trained a model that says, hey, I don't know what this is, by literally changing 2 lines of code, right? Because all we really changed was this and add a function. Or if we go down to the datasets part, we brought in what we knew earlier and added this function here. Does this sort of make sense from an idea standpoint? Or is there some place that I can explore this a bit further before we go over to cross-validation and ensembling? We'll take a moment for folks to ask questions, because this is a really interesting idea that Jeremy didn't even include in the course until I think the latest iteration, after seeing that I had done it, because enough people had asked, how do I do this? And it's such a very beginner question that it's important, I think, to approach fastai and the data block API with a thinking out of the box perspective, because it can lead to ideas such as, oh, hey, what happens if I do this? And Jono made a good point of our accuracy is really high because predicting all zeros with n classes, right? So we only have one class here, gives an accuracy of n minus 1 over n. So it got 9 out of the 10 right. And then if it missed 1, then it's like a 5% drop, for instance, if we had 20 classes, which is right. That's why this looks so high, because at this point it's saying, okay, we missed one label X amount of times, but we got the other 16 right. So someone asked, please explain further, how does multi-category come into play? I can try and reiterate sort of what's going on here a little differently. So what the multi-category lets us do is it tells fastai to use the multi-label classification loss function. And that loss function has a particular set of decoding on those predictions that I mentioned earlier in the previous notebook. That's different from cross-entropy, because cross-entropy loss flat goes, okay, this is my loss function. You're doing single label classification. So when I decode our model outputs, I'm going to take the argmax of them, or what had the highest probability, and that's my index. Whereas with multi-label classification in the framework, it uses a different loss function, which has a different decodes that can take our problem and convert it into multi-label. Now, the answer to do this on an already deployed model is when you're decoding your predictions to just treat it like it's that sigmoid from earlier instead of taking the argmax. I haven't actually experimented with how good that is in practice of if you train for multi-label classification or not. My intuition tells me it'd be probably kind of similar, but with this one, you can stay in the framework if you wanted to, during training at least, to get that quickly done and just have it be confident that, okay, I know that it's having this behavior and doing it well. And then if it does, we'll migrate over to cross-validation. All right, so now to go from classification to a training paradigm. And this is going to be what is called cross-validation and ensembling. Now, what that basically means is rather than training one model, we're going to train a number of models. These number of models are equivalent to what we call a fold. And each fold basically means, so if we take all of our data set, okay, and chunk it up into 9 separate parts, or 10 separate parts, for instance. So like 10% for each one. What I can do during cross-validation is say, okay, I have 10 validation sets, each of them being that 10% chunk, with 10 models that are trained on one of these validation sets. And so their training data set is the other 90% that wasn't part of it. So each model sees a different validation data set and a kind of different training data set. And at the end, we take all their predictions in what's called a voting ensemble, where we take the average of all their predictions for a particular image. And generally, this performs better than just a single model because you are able to train on more data. Different models were able to look at different things. And so as a result, you sort of get a stronger comparison of what's going on at the cost of doing inference is going to be longer and doing training is going to be longer because we're not training one model anymore. We're training 5, 10, or 20 models, one for each fold. Now, for this problem, we're going to be doing what is called a stratified k-fold. And the stratified k-fold basically says, we're going to create 10 subsets of validation data, but we're going to try our best to maintain the distribution of the classes in each of those data sets. So if the distribution is fairly normalized, then each, for the number of occurrences of, say, 10 classes, then every single folds validation set should also roughly fit this curve. So we're going to bring back in the stuff from before, right? Bring in our path, our file names, forms, all that stays the same. However, we're going to use a new splitter for this, the index splitter. And another important note that I've highlighted here is, so I mentioned that we have 10 different validation sets and basically 10 different training sets. So how do we know if something's, because we've sort of eliminated the right answer, right? The validation set and what it's there for. So when you're doing k-fold, you want actually 3 data sets. Your training and validation, and then a test data set. And the test data set is the same across every fold, and it should never be validated on until the very end of training. And the reason for this is, say as a data scientist, you notice that of your 3 models that you're going through, one model does really well on the test data set. And so you just stick with that model. That's actually bad because in practice, you don't have a test data set until it's deployed, really. And so the test data set is strictly there as a final test grade of here's how you did at the end of it. And we don't use that to then go and modify how we're training to overfit it. We don't overfit to the test data set, we fit to the validation data set. Because otherwise that leads to problems like data leakage. You're trying to fit for something and in reality it's something else. A prime example of this is, so I mentioned this is commonly done in Kaggle. In Kaggle, you have the public leaderboard and the private leaderboard. Now, you don't get to see what was right or wrong. You only get the answer after you've made a submission. It's kind of like our test data set here. But to go even further than that, there's a private leaderboard as well. And sort of what happens is a small subset of the data is the public leaderboard. And then the rest of it is the private leaderboard. And so if you are training to get the best score on that initial test data set, you might be completely wrong once you get to the second test data set that's the rest of it. And so it's extremely important to just focus on the validation data set when you're sort of tweaking things and want to make sure if this is right or not, and not overfit and train to the test data set at the end. Because the distribution in the scores between each model is not bad. In a lot of cases, it's actually very good if they're quite different, because that means each model was looking at something very different. So similarly to all our other problems, we're going to create some splits. So I've taken the file names, took 90% of them. That's going to be our train and validation sets. And then our test data set will just be the last 10% of file names. We're going to create a vocabulary for all of our labels. Very quickly, you can either do this or you can do this as a pipeline instead. Actually, this one gets the vocabulary. This one is our converter. There's a little tidbit on pipeline here, but we've kind of already gone into that some. This just gets our labels from the pipeline based on the file names. And then we're going to create an instance of the stratified k-fold object. Now, what we're essentially going to say is how many splits we want and whether or not we want to shuffle the training indices as we're going. So should they all be in order or should we shuffle them? I'm just going to shuffle them because more random is generally better when we're dealing with stuff like this. And so when we're creating our splits or our splitters, index splitter only cares about the validation indices. So we call the stratified k-folds split function and give it a number of items equal to the length of our data set and our labels. And this is what it's going to look at when it tries to figure out this sort of distribution. And then we'll create 10 splits off of that. Someone asked a question of, besides Kaggle, do you recommend doing cross-validation? The fastai, of course, doesn't mention it. It doesn't. That's why it's in here. It depends on what you can afford. And I don't mean monetarily. I mean time-wise. Generally, cross-validation will perform better, but it comes at the cost of time. And so what matters to you is the size of the model, how long it takes to do the inference, and if the gain in whatever metric you're doing on is worth running 2 models or 3 models or 5 models for every prediction instead of one. So there is no like yes or no if it's right or good or not, dependent on how your particular problem is situated to if it's valuable enough to explore across. So the next part we're going to do here is a little different. We're going to create a training function that takes a splitter and will perform our splitting for us. Test preds was declared outside of this function, and it just adds the predictions at the end to it. But basically, we built some data sets and data loaders off of our splitter. And in this case, I'm training for a single epoch just to show you what it's like. You could do fit fine tune, you could add more to this, you could unfreeze, freeze, change the fit function, whatever you want. But this is basically going to be all of your fitting that you want for a particular fold. And then we're going to store away our validation percents so we know how each fold did on the validation set. We'll create a test data loader off of our test set, get those predictions, and store them away for us to look at later. And so to train, we just say for every splitter in each of our splits, train. And you can see that it trains 10 times. And in some cases, our accuracy is better or worse than others. This isn't anything we can necessarily go off of because each validation set is different, right? But we can see that maybe some validation sets are easier than others for the model. Like this one was able to get to 89.7%, whereas some are a bit harder, like this one that only got to 87.2%. So you can eyeball it when coming from the perspective of how different is each fold and its relative difficulty, but this isn't a general idea of how overall it might, right? Because we had a highest of 89.7 and a lowest of 87.2. So let's sort of perform this ensemble now that we have 10 trained models. So when we do this, basically we take the average of all of their predictions. That is this equal voting, essentially. And to get the accuracy of one fold, this pipe is basically getting our labels from earlier and converting them into encoded items for us to use off of the test file names, since we don't really need to create a whole test set. We just need to know what the encoded label is. And this gets the accuracy off of the first fold for our labels. As you can see that it's about 88.7% on the first fold. And in our case, we actually have some cases where it goes up to 90% accuracy on our test set. So that's neat. That's actually really cool because that means the test set is maybe a little bit easier than our validation set was. So let's see how the ensemble does. So to do the ensemble, we call torch stack, pass in our list of predictions, and say we want to stack it on that last dimension, sum it based on that last dimension, and then divide it by the number of votes here. Now, this should actually be 10, not 5. That is a slight error since we have 10 here. But even based on 5, we can see that our new accuracy is 92% and it improved. If you guys want to, before I get to it, if you want to convert this to 10 and see if it still improves, which it should, you can try that out. But generally what you'll find is ensembling will garnish you 1 to 2% more, depending on the problem. Might be higher, might be lower. It just depends. There's a few other tricks you can do, like test time augmentation. I'm not covering that in this course, but basically test time augmentation is a mini ensembling where we apply the training augmentation to 4 folds and the validation augmentation to 1 fold and run that during inference. So not during training, only during inference. And getting these new perspectives on the image can also increase how your model does. But yeah, so sort of to end it on this, when coming to figure out if you should do cross-validation or not in these folds, basically it depends on should you or do you have the resources available and the time available for you to take these ensembled models in production and get back predictions at a reasonable time frame. And further, you can do that with test time augmentation instead, because the nice thing with that is you're not training multiple models, it's off of one model and sort of garnishing some of the benefits of it. But that's basically this lesson for today. It's not very long. I mentioned that the rest of the lessons aren't going to be too long from last week, and that's going to be the case for kind of the rest of the course. Next week, we're going to talk about semantic segmentation, and this other pre-trained models is basically TIM, and showing how fastai creates the TIM models with different heads and so forth. Lesson 5 should be chunky. This is going to be very interactive with us deploying fastai and PyTorch in Hugging Face spaces. So this one will probably be a bit longer. And then lesson 6 and 7 shouldn't be too long. 6 is just going to be some presentations for a bit. And 7 is going to talk about fastcore, fastai, and a little into NBDev. So if you want to build off of any data sets you were playing with or go through the previous lessons and try and do cross-validation on those data sets and see if it winds up beating the score that you got, that'd be a pretty good homework assignment for you to do to get used to this whole cross-validation idea. You can also look at Kaggle notebooks that talk about different validation techniques, because I just showed the stochastic k-fold where it keeps the distribution, but there's other ones as well, such as how does that differ a little bit when you have, say, labels that aren't that present, right? And you maybe need to do oversampling. How does that apply when you're doing cross-validation? So those are a few different homework ideas for you guys to think on. But otherwise, please fill out the form for this week so that way I can get some feedback on how it did. I know this week wasn't too long, but hopefully you guys enjoyed it and got something useful out of it, and maybe something new you didn't pick up on the first course.